Well, I'll start by thanking Mariana, Alvaro, and Nico for the very nice workshop and for inviting me to speak here. Very happy to be back here in Sacramento where I did my PhD. I'm going to be talking about non-supersymmetric strings and rank reduction. Most of the work for introducing this kind of thing was already done by Miguel and by Huri now regarding asymmetric orbifolds. So let's see what's the deal here. So the basic question is, how can we understand, let's say, the salient aspects of non-supersymmetric strings in simple examples, okay? And this includes, so you can have in your mind the non-supersymmetric heterotic strings, compactified on circles and analogs of that. And here I'm showing you two pictures that are from this recent paper. By the way, this is work in progress and some work I did with Bernardo. But this is related to this work with Mariana, Sav, and Bernardo of compactifications of the non-supersymmetric heterotic strings. And what I want to show you here is like this. You can think of it as a moduli space classically, but of course you have a potential because the theory is not supersymmetric, but still you preserve many properties that you see in supersymmetric strings, like for example symmetry enhancements, but of course now you have tachyons. This is a common problem. But see here, this is very nice. You have enhancements, and there are maximal enhancements here that they extremize the cosmological constant. This was shown by Ginsburg-Baffa. I didn't put the reference here, but this was shown by Ginsburg-Baffa back in the 80s. Okay. But now we have matter content because the theory is not supersymmetric. Okay, this is something I would like to understand for many theories. Another thing is I want to classify them. And why do I want to classify them? Well, because you keep constructing new theories and new theories and new theories, but do you know if you're finding the same thing over again? So if we have some classification scheme, then that would be good. So we can cut redundancies. And this is something feasible if we find relations among them. Okay. And the other thing is, can we see some inherited properties from supersymmetric strings? And here I want to talk about the duality. I will talk about it at the end of the talk, which is a kind of controversial thing, but it's fine. But I will restrict to spontaneous supersymmetry breaking, something like Serre-Schwarz reductions. So explain a bit more about that. Okay. So, and these are theories that descend from theories with 16 supercharges. That's why they are preserving so many nice properties. Okay. Okay. Let's review the supersymmetric case. Okay, so if we have theories with 16 supercharges, as we saw in earlier, they have many nice properties. It allows us to study them in a very controlled manner. They can in particular be realized by taking the heterotic string and doing asymmetric orbifolds, like Huri explained. But in this case, we want to preserve supersymmetry, 16 supercharges. And you can also do it by breaking half supersymmetry in type 2 strings. Of course, there are many other constructions, like geometric constructions, type 2 and K3 and so on. But I believe they all have a asymmetric orbifold corner. There's a lot of evidence for this. And each one of those constructions will lie in a disconnected component of the moduli space that is characterized by the rank of the gauge symmetry. Okay. Now, if you go to a dual frame in 7 dimensions and 8 dimensions, like you take a theorem theory, you put it in a K3 surface, then every non-component of the moduli space is captured by freezing singularities. So you can freeze singularities on the K3, and you get everything that we know. And these frozen singularities, there was a bit of an explanation before what they are, but you can think also of them as generalizations of orientifold planes with positive charge. Okay. And when you have these frozen singularities, because you know you can freeze them, then you can do a formal mapping of the main component of the moduli space with full rank to those with rank reduction. Okay. These series with rank reduction, they exhibit other interesting properties beyond just classification purposes, like having non-simply laced gauge symmetries or higher levels in their gauge algebras and so on. So this mapping of the gauge symmetries was done for 8 dimensions in the heterotic string with respect to the CHL string in this paper by some authors that are here. And then I extended it with Bernardo to other cases with frozen singularities. Okay. Here I want to show you this a picture in 7 dimensions of all the moduli spaces that we have. The red letter here is the rank. The letters here, they represent ADE, frozen singularities. And I just want to emphasize that we can start from here and go to every one of them using some special map. And here, just to remind you what is the form of these moduli spaces, the cosset spaces, quotiented by some discrete symmetries, though I will not enter much into detail about this thing here. Okay. All right, if we go to 6 dimensions, we don't have any physical way of realizing a map analogous to this, but we can be smart and formally generalize the map looking at properties of these theories. And what we found is that actually the map has a nice action on the gauge symmetries, and it acts depending on the topology of the group. So anytime you have a gauge symmetry like this, you can think of the heterotic string. The 10-dimensional heterotic string with this gauge group is not a SO32, it has a set 2 here. And then you go to 6 dimensions. What you can do is say, well, this set 2, it defines an automorphism of the linking diagram that you can then fold, and you get this group, which is not simply connected, and it's spin 17. And this defines a group in a different component of the moduli space. You see here very explicitly that the rank reduction is by 8, so this has to be the CSL string. Okay, so we recover the CSL string using this kind of formal rule. There are other examples, like if you start from E6 times E6 times E6, and you have a set 3, this thing will act on each one of these factors and give you G2, 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 you reduce the rank by 12, and then this is set 3 triple. So it's another component of the moduli space. The point is that you can then think, okay, maybe I can do this in any way that I can, in any way. And I will, if I do that, I recover every known component of the moduli space, okay, and with 16 supercharged in 6 dimensions, and then I can predict others, which is what Miguel mentioned earlier. But here I want to be a bit more conservative because there is a class of compactifications that are only cyclic orbifolds, and those are better controlled. Non-cyclic orbifolds are not well explored, and the non-cyclic ones are those that you need in order to realize odd rank in 6 dimensions. So this is not part of the discussion here. Now, another very interesting property of these theories is that if you compactify them to 2 dimensions, you put them on a torus, so you are preserving all the properties, you compactify them to 2 dimensions, and you do variations of the moduli, you do some marginal deformations on the worldsheet, you can see that there will be points where the partition function will factorize holomorphically. So this is a cartoon of the moduli space in 2 dimensions. You always have these points here, where the partition function is of this form. And then you can say, okay, if a partition function looks like this, I have a potential for doing a classification, because this left-moving CFT, for consistency, it has to be a bosonic. In the case of heterotic strings, it has to be a bosonic CFT with central charge 24, and these things were classified as Shellekens back in the 90s. So, and if it's type 2, then you need C equal 12, and this has to be a theory with 24 real fermions and a particular choice of current algebra. And you can see some nice things about these tensor products in this relatively recent paper. Okay. So here, part of what I want to think also is that the Shellekens list, if you look at Shellekens list and then you turn the problem on its head, you can see that there are missing string theory constructions in 6 dimensions that would fill out this thing. And then we strongly believe that those theories should exist. Okay. Another very important point is that these CFTs, they are not just some tool to do classifications, they actually encode information about the 6-dimensional theories, and they encode every possible gauge symmetry that you can have in 6 dimensions. Okay, so that's an important point. I will explain a bit more about this later on. Okay, so this is the big picture in the non-supersymmetric case. Okay, I have a classification scheme for these things. And this includes any theory with 16 supercharged 6 dimensions. Okay, so let's see about the non-supersymmetric case. Okay, the question is there an analogous story for non-supersymmetric strings? I think there should be one way or another, and the reason is simply that non-supersymmetric heterotic strings exist. So these theories, when you look at them classically, as I said before, they look very much like the supersymmetric counterparts, at least classically. So they share so many properties, and since you can do asymmetric orbifolds in the supersymmetric strings, you think maybe we can play the same game here, okay? And all the structure that I mentioned, there should be something analogous to it. Okay. There is a clue to realize this goal, and it's to remember that in 10 dimensions, supersymmetric heterotic strings, they are given by bosonic CFTs with central charge 16. There are only two of them, E8, the one with current algebras E8, and SO32. So you can kind of have your classification in that sense. But the non-supersymmetric ones, they are related to fermionic CFTs, okay, which are less constrained. And you have 7 of them. So it follows that you have 7 non-supersymmetric heterotic strings. This relation was explored and treated very carefully in this recent paper. Oh, sorry. In this recent paper. So then the point is that, of course, if I'm going to play the same game as before, I need the classification of theories fermionic CFTs with central charge 24, which is a much more difficult problem. Okay, but fortunately, this was achieved very recently in the mathematics literature by Ho and Moller. So what they did there was basically do the same that Tachikawa and company did here for some fermionization procedure applied on the bosonic theories, but going up to C equal 24. And they find 969 CFTs of this type. They are arranged into 33 families. And each one of those families can be then associated to a two-dimensional moduli space for non-supersymmetric heterotic strings. Okay. So let me explain this a bit more in detail. This picture here is central to all the discussion. So what does this represent? You have lots of nodes labeled by letters, and those nodes, what they are families of bosonic CFTs. Each one of those families corresponds to many points of factorized CFTs, and they in turn correspond to a moduli space of supersymmetric heterotic strings. So for example, this one here, A, is just take the heterotic string, put it on T8. You have two-dimensional theory with 16 supercharges, and it's here. Okay. And there are many others, like the CHL string corresponds to this, which is a set 2 orbifold, and then you have many other things, like the triples of triple fluxes and strings, like every orbifold that you can get in high dimensions, it should be here, and it is here. So then we have links, and what those links represent are non-supersymmetric. So they represent here in the formalism of CFTs, they represent the fermionic CFTs that you can obtain from the bosonic ones. So there are 4 kinds of links. They are called 1, 1A, 2B, and 1 to A, 2B, and 3 by Ho and Moller. And there are families of fermionic CFTs. So, for example, here, those like A1 here it will correspond to the O16 heterotic string compactified on a torus. Now, all the rank 16 heterotic strings are T-dual. So here is you think of those 6 non-supersymmetric theories that are all encoded here. Okay. All of these theories, the worldsheets, they are constructed using -1 to the f, like the shared source reduction, the usual shared source reduction, but you accompany it by an automorphism of the charge lattice of the theory. And then there are different kinds of shifts that you can do. I'll explain in a second. So the conjecture that I have, and I'm very confident of, is that all of these theories, the non-supersymmetric ones, will also uplift to 6 dimensions or more. So it gives me a classification of those theories. Okay. And the intuition behind that is that to construct them in 2 dimensions, you can do that. And this requires outer automorphisms. And then those automorphisms, they have to uplift to 6 dimensions, and then you can apply them there to get the 6-dimensional theories. Okay. And so another important point is that if you take something like the CHL string, the charge lattice is more complicated than the Narayan. So you can shift in different ways because you don't have all the idea is this. You have a charge lattice that is not self-dual, so you have different kinds of vectors, and if you shift along those kinds of vectors, you get different theories. But doing that is very challenging. It's not that trivial. I'll explain a bit more in detail what each one of the letters mean. You have class 1 theories. I call it them class, not to use too much the mathematical jargon. So let's call them class 1. They are genera, but let's say class 1 theories. They are shared source reductions. So let's say you take the CHL string, you do a shared source reduction, you put it in a circle with antiperiodic boundary conditions for the fermions. You get B1, which should be right here. Okay. class 2B theories, they are like non-supersymmetric versions of the supersymmetric ones. So what that means, you have the supersymmetric theory, it's defined by some kind of orbifold, and then you attach an extra -1 to the F there. This will break supersymmetry. And a nice example of that is the so-called non-supersymmetric CS shell string, which was constructed and studied very in depth by Nakajima this year. And there are those versions, you can find them for many other supersymmetric theories. The class 3 theories, they do not involve shifts. So they're like the EH string. The EH string is here, it's B3. And the class 2A theories, they involve other kinds of shifts, and they're not much explored. But something that one can check is that the B2A will correspond to a shared source reduction of the EH string. It's weird doing a shared source reduction of the EH string because it's already non-supersymmetric, but you get another non-supersymmetric theory. And this fills the classification. So if you have a non-supersymmetric theory constructed along these lines and has rank reduction by 8, then it has to be here. Okay. How do you prove this? Well, you have to do a computation. So you need to compute the partition function of these theories that I mentioned here. Then you have to play around with it, do some deformation of the moduli, factorize it, and then match it with the data of the partition functions presented in this classification. And it works. Okay. Now, the classification seems to work fine, but what can we get from it? So, can we get spectral data of the 6D theories? Let me explain what I mean. If you have a heterotic string on T4, you have type 2 strings on K3, then it is a fact that every gauge symmetry is encoded, let me restrict to non-abelian gauge symmetries. All of them are encoded in the 24 Neumayer lattices. These are the lattices that underlie the family of associated CFTs. I'll give you an example. So this is the Neumayer lattice 3E8. You write down the Dinkin diagram. You take out 4 nodes. This is the prescription. You take out 4 nodes however you want. You get something, some algebra. And this has a 6-dimensional realization. You do this for all the Neumayer lattices, you get everything. And this is valid for every other component of the moduli space. Now you can ask if this is also the case for the non-supersymmetric counterpart, for the 16 on 16. It's a bit more complicated because you don't have 24 lattices, you have 273. Okay, each one of them corresponds to a fermionic CFT. But you can prove, starting from the knowledge that this works in the supersymmetric case, you can prove that this also works here, which is more interesting because you don't have only vector multiplets, you also have matter. You have matter content, so you have gauge bosons, you have matter content, and you have tachyons. You can have tachyons in these theories, and great part of the spectrum will be encoded in those lattices. An application of that is if you want to explore the space of all of these compactifications, you want to check for extremal points of the potential, then you can really make that job simpler here, though it's something to be explored. For the other non-supersymmetric theories, it's much more difficult to prove it, like analytically, but it seems feasible to do with the aid of computational methods. But it seems that all those supersymmetric aspects that we have are also here in this case, in this family of theories.
Sorry,
yes.
Why can't you remove 2 nodes from one, 2 nodes from another, and 0 from the third?
You mean, sorry, you can remove any kinds of nodes that you want. You can remove.
Okay, so these are just 3 examples.
Ah, there are 3 examples.
Okay.
From.
Yeah.
Okay. Okay. Now, is there some? Okay. Let me go with time. Okay, it's fine with time. Rank reduction and duality. So I say that it would be nice to have a rank reduction map in these non-supersymmetric theories. I think it's a good thing to have because then you can very easily produce the spectrum of these theories. But remember that those maps have a physical realization as frozen singularities or identified planes, things like this. So if we had something here that we could prove formally, then it might have some physical meaning. Okay. Let's think about it just formally. The challenge is that since the spectrum has different classes, you have gauge bosons here, matter there, and each one is related to different subsets of the charge lattice of your theory, it really doesn't seem to make sense to to take two theories and embed the content of one into another. How do you do this? It's not clear. Yeah. And there's another problem, which is perhaps deeper, that, as I said, the rank reduction maps are meaningful as singularity freezing in MF theory, but I'm not doing M theory, I'm not doing F theory, I'm doing heterotic strings. It's perturbative. Okay, so we don't have such a dual so far. Maybe they don't exist, I don't know. In the non-supersymmetric case. And in general, there's very little known about string dualities, string-string dualities. There were some attempts at constructing them back in the 90s for the SO16, SO16 string, for type 0 strings, things like this. But it's really murky. It's not clear if these dualities actually work. So let me think here of a first step with these rank reduced theories. Maybe we can find an orientifold that is dual to one of them. And I want to propose such a thing. Okay, and we start with the CHL string. Okay. So the CHL string, it has an orientifold dual in 8 dimensions. So you take type 2 theory, you do an orientifold, and you put, you usually would put 4 or 7 minuses. And this would be dual to the heterotic string on T2. If you then, and of course you need a number of branes to cancel the R tadpole, but if you exchange one of those orientifold planes and some branes by an O7 plus, then you reduce the rank of the theory because you have less branes, and you get a dual for your CHL string. Okay. Now, in this special case, you can break supersymmetry by conjugating the RR charge of these two orientifolds. Okay. So you exchange these two guys by anti-orientifold planes. Okay. Now you still have 87 branes, so they are not mutually BPS, and supersymmetry is broken, but you don't have a tadpole. So you don't have a 3-level energy, which is something that is usually in brane supersymmetry breaking constructions like this. And this is a model that was put forward by Kurdashev, Dudas, and Partouche in 21. I didn't put the date, but it's fairly recent. It's 21. Now, the spectrum of gauge bosons is not altered. Okay, you still have the same gauge bosons, but the spinors they are altered, and so they go now to symmetric or antisymmetric representations of your gauge group. And this is a fact of the spectrum. But the interesting thing is that if you take the CHL string and you break supersymmetry, this non-supersymmetric version of the CHL string, you get exactly the same behavior at all points in the moduli space here, except for the fact that now you don't have fermion singlets. Okay. So here in the symmetric and antisymmetric representations, they are reducible. They have singlets, but you don't find them in the non-supersymmetric heterotic string case. Other than that, the spectra match perfectly, and I think this is the best example of a string-string duality so far. So I think it's very likely that these two theories are strong, weak dual. But then not all the mass spectrum is preserved. You have some singlets that are not in one frame but are in the other. And so if you have a proposed map that will connect the different theories, it will depend on the duality frame. So that's very different from the supersymmetric case. On the other hand, you can extend this to type 2 constructions, because you can play a game where here, let me show you here, you can then exchange this O7 minus for an O7 plus. You can do also here, and you reduce the rank, but that's not heterotic. That's type 2. And so that's very nice, because it allows you to extend the classification of heterotic strings. You connect them with type 2 strings, so you have a bigger picture. And even more so, this, I think, gives evidence to the fact that strong weak duality makes sense in a supersymmetric string. So perhaps the ones that were proposed, they are actually good. At least, but in this case, at least for freely acting orbitals. So you could have a more complicated story. And another point that might be more interesting phenomenologically is that you have access to the potential at two asymptotic regions of the modular space of this series. So maybe you can say something meaningful about the potential in the full modular space. So it's a bit more conjectural. So I'll just leave these things here. But let me first finish. So thanks for your attention. Let me just use this points here. Yes.
Thank you for the nice talk. So, do you mind going back to the mapping with the duality? And you were saying that the fermions were different. What was this?
Sorry, what? In the non-supersymmetric case?
When you were there's a 7 case. You were saying that the spectrum is the same bosonic spectrum. And how did the spinors are the only ones that were different, right?
Yeah, the gauge bosons are the same.
And you're saying
so
that
the gauge symmetry is the gauge algebra is the same.
Okay.
But in the supersymmetric case, you have adjoint fermions because they are the superpartners. But then you break supersymmetry, and here the story changes. So here you still have O7 minus, and you put the difference on top, and you still have adjoint representations of the fermions.
Oh, I thought you said that they're different, the two duality frames, not different.
No, okay, when you break supersymmetry, you change the spectrum.
Oh, that's what you meant, okay.
But then in the two frames, they will be different just by the absence of a singlet. So it would be that you have a massless state appearing at strong coupling in the heterotic case.
Okay.
That's the same.
Okay, that's okay. Thanks.
Thanks for the very nice talk. So I wanted to ask the classification you have of bosonic CFTs, fermionic CFTs. The thing they have in common is that they have current algebras that saturate the central charge of the CFT, right? That's how. So it's like you're classifying things which have a covering which is at torus, like a TN or.
Yes, essentially.
That's the physics intuition of it. Okay.
Yeah.
And also I had a question about what Julio was asking about the fermion singlet that appears or disappears. Can you see? I mean, that makes sense because like singlet fermions, they can get a mass, they can become heavy as you go to different corners of the duality. But it would be nice to see if you could like recover the mass term for it and see it appear in one limiter.
Yeah, no, I agree. That would be very interesting to understand. Thank you.
I can speak loud.
Okay.
Can you,
For the Zoom. It's for the Zoom.
okay. Thank you.
Yeah.
So in these dual pairs that you discussed in the last slide, next to last, how do you get symplectic groups in the heterotic?
You get
because you can move branes wherever, it depends, I mean, which planes you put, you can get orthogonal symplectic groups, as you said. But
yes, this already happens in the supersymmetric case in the CSR string in 8 dimensions. So, sorry, the question is how do you get them?
It's in heterotic.
In heterotic, it's because when you do the orbifold, you get when you look at the untwisted sector, you have short roots, but the untwisted sector can give you long roots, and then they can combine, and this gives you non-simply connected, non-simply laced groups, and in this case, it's symplectic.
Even in type 2, you can get this. 4 dimensions.
But here you're not doing orbifold, so you're using this classification.
Sorry, here? Yes. For the non-supersymmetric, I'm doing orbifolds. Yes. Right. Yes. So I use the classification. I have the classification, and then by hand I construct the orbifolds, and then I match the partition functions. So then I see that the classification actually works. But I have the orbifolds for the rank 8 rank reduced theories.
Any more questions? Not then.
So they all have they all have tangents at some corner, right?
All of them, yes.
You couldn't find, okay, but does it have enough directions that I can potentially introduce shift?
All of them have region. Well, E8 string has tachyons everywhere. The E8 string. You compactify, you have tachyons everywhere. All the other strings, like this class 1 to A to B, they have regions with tachyons, they have regions without tachyons. So now the question of stability of those.
They depend on the radius or something.
On all the moduli, radius, Wilson lines.
Consider probably going to some point.
Yeah, you can go to a tachyon-free point, it's not a problem.
And this is a reduction of the E8, also has tachyons everywhere.
The reduction of the E8 has one tachyon in all the moduli space.
Okay, so wait.
Okay,
Yes, okay.